What if I told you that engineers can see inside solid metal, without cutting it, without breaking it, without even scratching the surface? What if a tiny device the size of a TV remote could detect a crack thinner than a human hair, buried 3 feet inside steel? That's not science fiction, that's ultrasonic testing, and today, we're going to break down exactly how it works, why it matters, and why billions of dollars of infrastructure around the world depends on it every single day. If you've ever wondered how engineers keep bridges, pipelines, aircraft, and nuclear plants safe without tearing them apart, you're in the right place. Stay with me, this is going to blow your mind. Alright, let's start from the very beginning. What exactly is ultrasonic testing? Ultrasonic testing, or UT, is a non-destructive testing method. That means we test materials for flaws or defects without destroying or damaging them. Think of it like a doctor using an ultrasound to look inside a patient's body without surgery. The principle is almost identical. Here's the core idea. We send very high-frequency sound waves, higher than anything the human ear can detect, into a material. These sound waves travel through the material, and when they hit something unusual, a crack, a void, a weld defect, a boundary between two different materials, they bounce back. We catch that reflected signal, and from the time it took to return, we can calculate exactly how deep and how large that flaw is. The frequency we use is typically between 0.1 and 15 MHz. For comparison, humans can only hear up to about 20 kHz, so we are talking about sound waves that are hundreds of times higher in frequency than the highest pitch you've ever heard. Now, why does frequency matter? Higher frequency means shorter wavelength, and shorter wavelength means we can detect smaller and smaller defects. It's like using a finer comb, the finer the teeth, the smaller the things you'll catch. This little device, called a transducer or probe, is the heart of the whole system. It does two jobs: it generates the ultrasonic pulses, and it receives the reflected echoes. It can do this because it contains a special material called a piezoelectric crystal. To understand how UT works, we need to understand two things: the piezoelectric effect, and how sound waves behave in materials. Let's start with piezoelectricity. The word comes from Greek. Piezo means to press or squeeze. When you squeeze certain crystals, like quartz, or synthetic materials like PZT, they generate an electric charge. And amazingly, the reverse is also true. Apply an electric voltage to these crystals, and they physically expand and contract. This is genius in its simplicity. When we send a rapid electrical pulse to the piezoelectric crystal in our probe, it vibrates at an incredibly high frequency, generating ultrasonic sound waves. And when those reflected waves hit the crystal on the return journey, they squeeze it slightly, generating a tiny electrical signal that our equipment measures and displays. Now, let's talk about sound waves. When a sound wave enters a material, several things can happen. First, reflection. At any boundary, like the back wall of a metal plate, or a crack, some of the wave energy bounces straight back. Second, refraction. When a wave crosses from one material to another, say from the probe into the metal, it bends, just like light bending through water. We can use this deliberately. Third, mode conversion. Longitudinal waves can convert into shear waves at an interface. This is critically important in angle beam testing, which we'll cover later. Fourth, attenuation. As sound travels through any material, it gradually loses energy due to scattering and absorption. This limits how deep we can test. Understanding these behaviors is what separates a good UT technician from a great one. The physics tells you where your wave is going, how fast it's traveling, and what the signal on your screen actually means. Okay, so you understand the science. Now let's look at the actual equipment. A complete ultrasonic testing system has 5 key components. Number 1, the pulsar receiver. This is the brain of the operation. The pulsar generates short, high-voltage electrical pulses. We are talking up to 400 volts in some systems, to excite the transducer. The receiver then amplifies the tiny return signals from the echoes. Modern digital instruments do incredible signal processing here. Number 2, the transducer, or probe. We've talked about this, it contains the piezoelectric element. But there are many different types. Lays out several probes. Contact transducers are used directly on the surface of the material. They need a couplant gel to eliminate air gaps. Immersion transducers are used when the part is submerged in water. Water itself acts as the couplant. Angle beam transducers have a wedge built in that refracts the sound at a specific angle, typically 45 degree, 60 degree, or 70 degree, allowing you to inspect at angles to find differently oriented defects. Dual element transducers have separate transmitting and receiving crystals, great for detecting near-surface defects. Phased array transducers have multiple crystal elements that can be fired in sequences to steer and focus the beam electronically, the Tesla of UT probes. Number 3. The couplant. Sound waves can't travel through air gaps effectively. A couplant, usually a water-based gel, oil, or even just water, fills the tiny gap between probe and surface to ensure good acoustic coupling. Number 4. The display unit. This is where you interpret results. There are 3 classic display types. A scan, a simple graph showing signal amplitude vs time. The industry workhorse. B scan, a cross-sectional image of the material, like a side view. C scan, a top-down plan view, incredibly useful for mapping large areas. Number 5. Reference standards and calibration blocks. Before any inspection, technicians calibrate their equipment against known test blocks with machined reflectors of known sizes. Without proper calibration, your results mean nothing. Types of ultrasonic testing techniques. Now let's dive into the different techniques. Ultrasonic testing isn't just one method, it's a family of techniques, each designed for different applications. Pulse echo method. This is the most common technique, and it's what most people mean when they say, "Oat." You send a pulse, you listen for the echo. The time between sending and receiving tells you the depth of the reflector. The amplitude of the echo tells you the size and orientation. One probe, 2 jobs. Simple, effective, and powerful. Through transmission method here, you place one probe on each side of the material. One transmits, one receives. Instead of looking for echoes, you measure how much sound energy makes it through. If there's a big defect in the middle, it blocks the sound, and you see a drop in transmission. Great for composite materials and adhesive bond testing. Angle beam testing. Remember mode conversion? By placing a wedge under the probe, we refract the sound beam into the material at a specific angle. This is incredibly useful for weld inspections, because weld defects like lack of fusion, cracks, and incomplete penetration are often oriented vertically or at angles. A straight beam won't find them. An angle beam will. Phased array ultrasonic testing, PAUT. This is where things get seriously advanced. Instead of one crystal, phased array probes have arrays of 16, 32, 64, or even 128 small elements. By firing each element with a slight time delay, called beam phasing, the system can steer the ultrasonic beam to any angle without moving the probe, and focus it at different depths. The result? You can scan a weld completely, from multiple angles, simultaneously, in seconds. And the data? It's displayed as a beautiful color-coded sectorial scan, like a radar sweep, showing you exactly where defects are and how big they are. Time of flight diffraction, TOFD. TOFD is a sophisticated technique that uses 2 probes straddling a weld, one transmitter, one receiver. Instead of just looking for reflections, it analyzes tiny diffracted signals from the tips of cracks. Why? Because diffracted signals appear even from very small, tight cracks that might not give a strong reflection. TOFD is incredibly sensitive and is also used to accurately size defects, critical for fitness for service assessments. Long-range ultrasonic testing, LRUT. What if you need to inspect hundreds of meters of pipeline, but you can't excavate all of it? LRUT sends guided waves along the pipe wall that travel tens of meters in both directions from the probe location. It's used to screen large lengths of pipe quickly, identifying areas that need detailed follow-up inspection. Revolution in the pipeline industry. How to perform a UT inspection, step by step. Let's get practical. Walk with me through how a real ultrasonic inspection is actually performed. I'm going to use weld inspection as our example. It's one of the most common UT applications in the world. Step 1. Pre-inspection planning. Before you even touch the part, you need a procedure. What's the material? What thickness? What type of weld? What defects are we looking for? What technique? What frequency? What probe angle? This all gets defined in a written inspection procedure, which must comply with the applicable code. More on codes in a moment. Step 2. Equipment setup and calibration. We set up our flour detector, connect our probe, and calibrate. Calibration means scanning the reference block with known reflectors and adjusting our equipment so those reflectors appear at the correct position and amplitude on our scan display. We set our DAC, distance amplitude correction, curve, which accounts for the fact that deeper reflectors produce weaker signals even if they're the same size as shallow ones. Step 3. Surface preparation. The scanning surface must be clean and smooth. Paint, scale, heavy rust, all of these interfere with the coupling and can give false readings or miss real defects. We clean and, if necessary, grind the surface. Step 4. Apply coolant. A thin, even layer of coolant is applied. In production environments, automated systems may use water as the coolant. The coolant fills microscopic air gaps between probe and surface. Step 5. Scanning. Now we scan. The probe is moved systematically across the inspection area, typically in overlapping passes to ensure 100% coverage. We watch the scan display constantly. Any signal that appears between the initial pulse and the backwall echo, and exceeds our acceptance threshold, is an indication. Step 6. Evaluation and sizing. When we find an indication, we characterize it. Is it planar, like a crack, or volumetric, like a pore? How deep is it? How long? We use the 6 decibels drop method, the 20 dB drop method, or sizing techniques like TOFD or PAUT to determine its dimensions. Then we compare against the acceptance criteria in our code. Step 7. Reporting. Every inspection requires a written report documenting all findings, their locations, sizes, and whether they were accepted or rejected. This report is the legal record of the inspection. Codes, standards, or certification. Let's talk about something that doesn't get enough attention, the regulatory world that governs all of this. Ultrasonic testing doesn't happen in a vacuum. Every inspection must be performed according to a specific code or standard. These codes define what technique to use, how to calibrate, what acceptance criteria apply, and what qualifications the inspector must hold. In pressure vessels and piping, think power plants and refineries, the dominant code in North America is ASME Section 5 for examination methods and Section 8 or Section 1 for acceptance criteria. For structural steel welds, bridges, buildings, machinery, AWSD 1.1, the Structural Welding Code, governs most UT work. In Europe, N standards and ISO standards apply. Globally, ISO 17640 covers UT of welds. ISO 9712 covers personnel qualification. Speaking of qualifications, let's talk about certifications. You cannot just pick up a UT probe and start inspecting. The people who do UT must be trained, tested, and certified to one of the major certification schemes. The most widely recognized system is ASNT, the American Society for Non-Destructive Testing, which has 3 levels. Level 1. Can perform inspections under supervision. Knows how to operate equipment and follow a procedure. Cannot write procedures or independently evaluate indications. Level 2. The core of the industry. Can write procedures, calibrate equipment, perform inspections, evaluate and interpret results, and write reports. Requires significant experience and passes written and practical exams. Level 3. The expert. Can develop procedures, establish and approve techniques, interpret codes, and train and certify Level I and II technicians. This is the top of the UT certification pyramid. Other major schemes include PCN in the UK, CSWIP in Europe, and COFREND in France. In high-stakes industries like nuclear, additional employer or industry-specific qualifications are required on top of base certifications. Like every technology, ultrasonic testing has both incredible strengths and real limitations. Let's be honest about both. The advantages: 1. It's non-destructive. You test the part without harming it. The part can go right back into service. 2. It's deep penetrating. UT can inspect very thick sections, several meters of steel in some applications. No other portable NDT method comes close. 3. Single-sided access. Unlike X-ray or through transmission, pulse echo UT only needs access to one side of the component. Critical for in-service inspection. 4. Real-time results. Unlike radiography, which requires film development or detector setup, UT results are immediate. The A-scan shows you results in real time. 5. Excellent sensitivity. Modern digital UT equipment can detect cracks and defects far smaller than any visual method. 6. Quantitative. UT gives you measurement data, depth, length, amplitude. Not just, there's a defect, but here's exactly how big it is and how deep. 7. No radiation hazard. Unlike radiography, UT uses sound, completely safe for surrounding personnel. The limitations: 1. Requires skilled operators. UT interpretation is not trivial. A poor operator can miss defects or create false calls. Training and experience matter enormously. 2. Surface finish matters. Rough, corroded, or painted surfaces impair coupling and reduce sensitivity. 3. Not ideal for coarse-grained materials. In materials like austenitic stainless steel or large castings, the coarse-grained structure scatters sound waves, creating noise that makes interpretation difficult. 4. Thin materials are challenging. Conventional UT has difficulty below about 10-6 mm because the initial pulse and backwall echo overlap. Specialized techniques exist but add complexity. 5. Only detects what it's aimed at. UT is directional. A crack oriented parallel to the beam might not reflect energy back. Technique selection is critical. 6. Requires couplant in most cases. Can be messy, and temperature extremes affect couplant performance. So there you have it. Ultrasonic testing, from the physics of piezoelectric crystals to phased array systems guided by AI. From calibration blocks to catastrophic accident prevention. From level I trainees to the most demanding inspection environments on Earth. Sound waves, invisible to the eye, moving through steel at 6,000 meters per second, returning information that protects lives, every single day. If you found this video useful, please hit like. It genuinely helps the channel grow, and it helps this kind of in-depth technical content reach more people. Subscribe if you haven't already, because we cover engineering, NDT, material science, and industrial safety in exactly this kind of depth. Drop your questions in the comments, whether you're a student, a working technician, or just someone curious about how the world actually stays safe. I read every comment and I respond. And if you want to go deeper, check out the links in the description. I've linked to the ASNT website for certification info, a recommended reading list on UT code references for ASME and AWS, and some great online UT training resources.